There's when you clicked it, the share button
I
appears.
have the same message. I cannot share. Look, I'm just going to send you the presentation, and then I can talk and tell you to get the next slide. I don't know how else I can. Huh?
Okay.
I simply don't know how to do this. I mean, it's so stupid. So can you see my screen now?
Yes, we can.
Yes, we can.
Okay, just to find how I can, just to see how I can operate this. Can you see this?
There's an infinity mirror.
Can you see my presentation now?
No, not now.
I don't know what to do. Can you send us Zoom link or something else instead of Google, because I don't know how to handle this.
For Zoom,
can we try to go on Zoom and you send to the participants Zoom, and then maybe, I mean,
in Zoom the participant number is limited, so we decided to make it in Google Meets because of that. So it would be great if you can share our presentation with us. I think Muhsin will help you with the presentation.
But I have problems. Just a moment. Entire screen. Then click this. Then share. And I have again the message that I cannot share. Just a moment. Let me try once more. So
you click the share button and select the presentation, and the share button doesn't the bold.
Actually, I first have to share entire screen. When I say share, it says I might have dismiss.
Did you select the entire screen?
Yes. You cannot see my screen. I don't know what's wrong with this. I'm sorry, but this is really weird. I cannot share anything.
Okay. If it is okay with you, I can.
I can send you presentation, but please don't share it afterwards.
Okay.
Because I mean, I'm just going to present the part of it. So it's really uncomfortable for me. Yeah. Okay. So I can try to send you this. Oh, it's pretty huge. I sent it. Did you receive that?
With email, I'm waiting.
I don't know why I have the issues with Google Meet, because I'm usually using it, but maybe, I don't know. Did you receive it?
Yes, I got.
So you can open it.
Let me download it.
While Mohsin is trying to open that, I want to thank you for your kind acceptance. We are really thrilled to be here with you today, and I hope it will be an instructive presentation for our participants. So we are also in and alive in YouTube. Thank you for coming here today.
Thank you.
Okay. Can you see my?
Yes.
Can you see the presentation?
Yep. So just put
Okay.
full screen.
Mm-hmm.
You go to
I will.
the slideshow.
Yes. Before I want to do some say something about. I want to introduce you to the participants. So after that, I will open that.
Mm-hmm.
Okay. Are we alive in the YouTube right now?
Yes,
Should
we
I
are.
start?
Yes.
Should I start now? All the participants all the participants attended?
I think they attended it to YouTube.
Okay. I will start. Dear neuroscience enthusiasts, welcome to our presentation. I am Musin and I am a second-year medical student at Ankara University, and I am happy to be here with you today. I also have privilege to serving as a co-leader of scientific team in our neuroscience community. We have been running a presentation series that covers a wide range of topics in neuroscience. And
And I'm Elif. I'm also a second-year medical student at Ankara University, and I'm the vice president of our neuroscience community. Thank you for your acceptance again. I hope it will be a great presentation for all of us.
Okay, today we are truly excited to welcome all of you with this presentation featuring Dr. Milena Cukic. We would like to extend our sincere thanks to her for being here with us today. We are honored to have her and we are excited to share her knowledge and insights with you. Before the presentation, I would like to introduce Dr. Cukic. Dr. Cukic holds a bachelor's degree in electronics and biology from the University of Belgrade. She later earned her PhD in neuroscience in 2011. Her research focused on analysis of neurophysiological signals, combining engineering with biophysics. From 2012 to 2015, she served as an assistant professor at the University of Belgrade. She taught courses on psychological complexity and neural networks. During this time, she also conducted postdoctoral research on vaccine development and tumor treating fields for glioblastoma multiforme. In 2017, Dr. Cukic founded 3EGA, a company dedicated to applying nonlinear methodologies for clinical decisions support. As a CEO, she led the development of techniques based on chaos theory and integrated engineering, neuropsychology, and biophysics. From 2022 to May 2024, she worked as a senior scientist at EMPA, Swiss Federal Laboratories for Materials Science and Technology. She led the digital twin for transdermal Fantelli therapy project and developed early prediction models for mild cognitive impairment. Currently, Dr. Cukic is a senior neuroscientist at ZHAW, Zurich University of Applied Science. Her research interests include fractal and nonlinear analysis of electrophysiological signals, digital health solutions, and non-invasive therapeutic interventions. With her experience across academia, industry, and in entrepreneurship, Dr. Cukic is a leading innovator in healthcare. Please join me in welcoming Dr. Milena Cukic to present on the importance of fractal and nonlinear characterization of electrophysiological signals for early detection tasks in psychiatry and neurology. And if you have any questions, feel free to write them in the chats. So, Yes. Can you see the presentation, whole picture?
Yes, you can put on slideshow now.
Oh, it's nothing. Then I should 1 minute. I should share the entire screen.
Mhm.
1 minute.
Yes.
Can you? Yes.
Okay.
Okay.
So I can start. Oh, thank you for having me. I'm Milena Cukic. It's hard to pronunciate my surname.
Oh, so sorry.
It's okay. And then can you go to the next slide? So I will have to ask you. So I just wanted you to see this because you're students and you're entering your experimental phase or research scientists. And I like those sentences because they are really having a grip on how we should feel. If you don't find something strange during the day, it hasn't been much of the day. This is one. And this is now my suspicion is that universe is not queer that we suppose, but queerer that we can suppose, meaning that you always have one picture and you expect something, but nature is so weird, it is going to surprise you many times. Next slide, please. So we are going to talk about this today. I mean, if you think of the pictures that I put on the screen, they don't have that much in common, like, cauliflower or leaf or neuron. They have actually something in common, and they are all fractal structures. Next slide, please. So today, I'm just going to talk to you about what is complexity. So I didn't put that on the screen, but all natural systems, forms, and processes are usually operating under complex systems dynamics. When we say complex, it means system which is comprising of several different things. For example, if you look at a brain, it is one of the most complex systems dynamics operating that we know for. And basically, interaction of the parts of that system are very important because the small differences and small interactions between the parts can actually change dynamics. Next slide. So, next slide. I'm just going to accelerate. So, if you're thinking about complexity, what is actually complexity? And you usually see variability. What is variability versus complexity? So, for example, if you measure one series of things, for example, the temperature, you will see that it varies over the time. But variability and complexity are two different things. When we say complexity, we mean a kind of characteristic of the system, and variability is usually binded to one kind of thing that you're measuring, one kind of process or dimension or something like that. Next slide, please. So this is very important man. He was a very talented, genial mathematician who actually compiled what mathematicians of 18th and 19th century were working on. And he was actually on the right place on the right time when IBM actually made first powerful computers. So he was able to generate some things which are known in mathematics for the last 2 centuries. So basically, Benno Mandelbrot was writing about fractals. And this is central tenet of my talk today because he coined that term. What means fractal? In Latin language, fractus means something broken. And he actually wanted to find a name of the system which doesn't have Euclidean number, because in Euclidean geometry, which every one of us learned in primary school, you have 1, which is something from the beginning of the line. Or if you have 2 dimensions, you have a plane. And if you have 3, this is a 3-dimensional thing. But fractal dimensions are non-integers. For example, fractal number can be 1.65. It is not 1, it is not 2. So that's why Benoit Mandelbrot was exploring fractal shapes and properties which are not abiding Euclidean geometry. Next slide, please. So I'm just going to explain to you what fractal structure means. For example, you also natural structures like a snowflake. And if you have a magnifying glass, you can see that there are really tiny, tiny structure below that. And if you use a microscope and increase the magnification, you can see that below that structure that you can see with naked eye, self-similar structure appears, meaning when you're magnifying, you're going to see more and more details, but they have very similar shape. So basically in mathematics, we have two kinds of fractal structure. Fractal structure can be exact. This is down left picture with Mandelbrot 3, meaning that when you're moving in different directions, you can see exactly the same structure. But in nature, for example, if you look pile arterial network or the shape of some of the neurons of our brain, like Purkinje cells, when you're moving in different directions, those structures are similar. They're not exactly the same. Next slide, please. So this is one of the first mathematical descriptions of the fractal. It is called Koch's snowflake. And you can see clearly here that you can generate from very simple structure. For example, you have a line and you divide it in three equal parts. And when you put the second line, you can see that this is the way how you generate more and more complex structure. And on the end, you have that snowflake. So basically, fractals also serve to illustrate how certain natural developed structure is filling up the space. Because basically, it can be really dense. For example, if you think of the magnifying glass looking at the surface of the brain, you look at that and you see very similar shapes and forms. And when you magnify that, you will see something similar, not exactly the same shape, but very similar to it. Next slide, please. This is another example, and this is basically about characteristic of what we call physiological complexity. I want to draw your attention to a name of late Professor Vladimir Shklonovsky, who actually wrote a lot about complexity in biological systems. And he said that complex structures and processes can have 3N. What does that mean? Physiological processes can operate far from equilibrium, then their fluctuations exhibit a long-range correlation, and underlying dynamics are usually driven by deterministic chaos. I will explain that a little bit later, but those 3Ns are, for example, if someone who is engineer and who is telling you something about signals says the signal is stationary, what does that mean? For example, it can be a current or a voltage or something like that. Stationary voltage means that when you are moving through the time and record that same thing, the variability is within some standard deviation, for example. So natural signals are not stationary. They change their characteristics over the time. This is first N. Second N, they are nonlinear. They are just not abiding Euclidean geometry. So what you learned from mathematics in primary school and in secondary school cannot be used to describe natural shapes and forms. This is a little bit more complicated. And then after nonlinear and non-stationary, this is also noisy. So if you had a chance to look at electrophysiological signals, like electrical signal generated by the brain or by heart or by muscles, they're simply not easy to analyze like generated current. This is the point. I mean, the signals which are produced by technological means, like man-made, cannot be compared, but the signals who are generating in living systems. Next slide, please. So I will skip that slide and the next. Let me look at this. So it is very important that you understand what we call linear and what is nonlinear. When we say linear, you have visualization of a line, let's say. But basically, when we have system and we say the system is linear, it means that it has additive characteristics. Life is not additive. You have a system like organism which consists of many cells and tissues and things like that, and they don't have additive features because those many parts interact, and that dynamic can be much more complex than simply additive mathematics, meaning that with classical mathematic means that we are learning in general, you cannot describe very complex signals which are coming from complex systems, because those elements in those systems interact and they have some feedback loops. Think about, for example, autonomic nervous system. Think about any regulatory mechanism in human body. They are not additive. They are not functioning on linear manner. They are usually non-linear. So life appears to be a non-linear phenomenon, right? So we go to the next slide. So non-stationarity versus stationarity are already explained, and I will repeat. When you have man-made signals like electrical current, it can be stationary signal. But when you record the electrical signal which is generated by brain, you simply cannot. You simply see with the naked eye that this is not linear thing. This is non-stationary, non-linear. Next slide. Next, okay. Stochastic versus deterministic. I have to explain something which appeared on previous slides. You probably heard about chaos theory, right? Chaos theory is actually complex system dynamics theory. This is just easier name. So what does that mean, word deterministic? It is something which doesn't change. It is predicting. Deterministic value is something you don't expect it to change when the time passes. So when we have deterministic equations, we are putting in equations something which can be described, calculated, expected, right? This is predictable thing. But stochastic thing is completely opposite. What does that mean, stochastic? It means it depends on what happens. You cannot predict that. So it is like you have two parts of the spectrum. On one side, you have something completely unpredictable, like chaotic nature, like stars, physiological processes and things like that. And the opposite side, you have deterministic, something which is predictable. So I would like you to try to associate everything which is man-made, that people make in technological sense, as deterministic, because when we have a generator which is going to generate the current, we want that to be predictable. And this is highly predictable system, which can be described with certain kind of mathematic formulas, right? And when you have something stochastic, you need probability system of mathematics to describe that kind of system. Life is somewhere in the middle. For example, think that you have very complex system. You probably think about the stars and planets and suns and things like that. And if you have more than two bodies which you want to know how they correlate, everything more than two constituents is really complicated to describe in mathematical sense. So in terms of describing in mathematical sense something which is a living system, we use something that we call deterministic chaos. What does that mean? I just said that chaos and deterministics are very opposite things. But deterministic chaos is something like current generated in the brain that you can describe with some differential equation, which belong to deterministic science. But then initial conditions can change that much that they can change dynamics. You probably heard about the butterfly effect. So, for example, this is applied on the first big studies of our climate, and this is deterministic chaos. You can describe equations, for example, how the temperature is changing, how the pressure is changing, how the air is moving. But then if you have a butterfly in Amazon flapping its wings, it can cause a hurricane to happen. And then in North America, you have disaster. So it cannot be predicted, but we understand that in nature, something really small can be amplified, and then you have something. I can give you one clear example, and I can use that to explain how we can detect that. Think about epileptic seizure. When you observe normal waves, normal EEG of the person who doesn't have that problem, they are pretty complex, but complexity, in my understanding, means health. Because in order to be adaptable to changes from your surrounding or your internal changes, I'm thinking in your body, your signals have to be a little bit predictable so they can shift to another operating manner, right? In epileptic world, actually, when we measure the features of that EEG, they become too simple and they actually amplify too much, and then the whole system is getting out of any functioning. So basically, epileptic seizure, I'm just going to show you another figure when you can see that, is actually opposite of the complexity. They are too simple to serve the healthy adaptability in the brain. Next slide, please. I already do that butterfly effect. So the next things. Next. So when you think about the word regularity, when you say that someone is regularly visit a place, it means that this is something predictable. Let's say that you have a friend who is going to certain club or going to school or going to certain places, and you cannot say, you can't pretty much say whether you can find him on certain location, right? So this also applies to the signals. Signals can be regular, meaning that there is no surprise about what is going to happen in half an hour, or in a couple of days. But signals who are biological or physiological signals are irregular. And they have to be irregular. As I said just a couple of slides ago, we understand now that the purpose of irregularity in signals that our body is generating is that we are able to change the operational manner. So, for example, if your heartbeat would be completely predictable and unchangeable, you would die if you try to run. Because in order to sustain other physiological processes, the heart rate must have much higher beat. It has to operate in completely different phase space. It cannot sustain just regular heartbeat because it is not possible. So that basically applies to any other physiological system. On the top of this slide, you see how that works. So let's think that we have some electrophysiological signal, let's say EEG or ECG, and how we can measure whether the signal is regular or irregular. We can measure whether it is more or less predictable. What does that mean? Those dots which are red, green, or blue, they represent kind of motif. Let's say that those three samples are once noted that they go one after another. And then you're going to go through the signal and see how many times the same motifs appears. So on this slide, you can see that that motif you have on the beginning and on the end, but you have those same values in different combinations. Let's say less than 3, 2, 1, or just one after another. So basically, how you measure that? You actually go through the signal and you calculate how many times the same combination of those values appears together. And then you can see whether they are more regular or less regular. It is the way how you can quantify that. Basically, you can see that after certain event or intervention, you can see whether the signal became more or less variable. So what does that mean? If we already know that healthy systems are exhibiting higher irregularity, then we can try to see how those people who are exhibiting some pathology are behaving. And usually they are not irregular. Let's go to the next slide. So, for example, you can see this is the first phenomenal application of nonlinear study. You probably heard about sudden infant death syndrome, when babies die in sleep. So basically, when they try to measure their heart rate, I can give you the clue. The lower one is healthy child heartbeat, and the upper one is child who escaped SIDS syndrome. So even with the naked eye, you can see that upper slide is showing less variable signal, right? You can see that this is not so rough. But basically, when you apply just regular statistics, those two signals cannot be differentiated because the difference is within one standard deviation. So you cannot say with standard statistics applied on this, that they really exhibit quantifiably different states. But if you calculate approximate entropy, this is one of the measures that I call nonlinear, because there are families of those measures. This is coming from statistical physics, and we can apply it in neuroscience. They're 3 times different, because the healthy child actually have much higher complexity and irregularity, and the child who is at risk of dying out of sudden heart event has much less adaptability to the events. Next slide, please. So this is another explanation of how fractal signals look like. I told you several slides before that you have 2 sides of the spectrum. On one side, you have completely stochastic signal, and this is down there. This is white noise. But physiological signal is obviously not stochastic. It is actually demonstrating that some electrical activity is actually reflecting the activity of the cortex of brain, let's say. This is, by the way, time series of heartbeat. So you can see that they are different, but you cannot describe that with the words. And I can reveal the feature. For example, if you do analysis of both time series, you can see 1/f. This is characteristic of natural systems. So for example, if you're not sure whether the signal that you have is generated by a living system, you can apply that kind of the test to see whether it has some internal structure. And another thing is also important here. If we are looking on electrical signal generated by the brain or by the heart or by the muscles, the bottom line is when you sample that, you have time series of certain values in, let's say, microvolts or something like that. So basically, if you try that on the upper time series and you change their order, you shuffle those samples, you will have the completely stochastic series, meaning that those values that you recorded actually depend of previous values. And if you destroy that internal structure of their history, you're losing the information about that system. Next slide, please. So why we are focusing on that? What is the use of that? Think about how any kind of clinician is operating. If someone is working in neurology, they can immediately say that someone has Parkinsonism, right? Why? Because people who have Parkinsonism are having the same feature. They have unwanted movement, they have a problem of having large steps, they have problem with equilibrium and things like that. So how we call that in medicine? Stereotypy of disease, meaning that classification of patients towards certain disorders that we already know forever are classified by certain features that they exhibit, right? But this is just visual, and you always have in any kind of ontology 10 or 15% of patients who are not typical. They don't exhibit all the clinical signs, and then you have a problem of classifying them, right? So basically, the whole field that I'm active in is using electrophysiological signals and nonlinear analysis to help clinicians how they can be sure to classify their patients. Let's say that clinician or cardiologist is not sure what kind of disorder is the reason of the suffering of that certain patient. And then he can describe that something is wrong with the muscle of the heart, or some maybe this is neurological reason that regulation of certain values is not proper, etc., etc. So basically, what we are doing here, I told you that if something is predictable, this is not normal. If something is unpredictable or irregular, this is normal. So we are basically trying to detect in electrophysiological signals if something is too predictable to be healthy. So basically, we are applying the same system like clinicians are always applying, and this is stereotypy of disease. When you analyze EEG of people who have some neurological problem, usually you can see by your measures and your calculations that they are too simple to be healthy. And we call that pathological decomplexification. Next slide, please. So there is a kind of difficulty to understand this, because I guess not many of you knew before this lecture what is a fractal, what is nonlinear. You're usually relying on mathematics, which is standardly taught in primary and secondary school, because you didn't go into mathematics, you went into neuroscience. But in order to use everything that we can in neuroscience, it doesn't hurt if you learn a little bit of the methods that they are applied in physics. Because, you know, in the beginning of the last century, medical doctors were called physicians. Somewhere in English-speaking countries, they are still called physicians. And the core of that word is physicus, meaning that physics is behind majority of physiological phenomena that we learn about today. Because when physiology started as a science, they use advances in physics to measure physiological phenomena, to describe them, and actually to learn how our body is functioning on physical principles. And physiology have a lot of in common with physics. We are learning our knowledge from physics to understand that. Now, if you want to advance the neuroscience and let's say analyze neurophysiological signals or electrophysiological signals in general, you should get a benefit from mathematics, which is used in statistical physics. And this is what I'm mentioning here. So basically, we already know that in order to function properly, the whole organism, the human physiology as a kind of science, operates in certain kind of complex systems dynamics roles, meaning the certain parts of that physiology have to be irregular to be able to adapt on the changes which are happening all the time. Although we don't like surprises, and in human psychology, I mean, we prefer things to be the same because we feel safe when we can predict something. But in physiology, unpredictable things are good. And you can see in many different descriptions of pathology that those systems are more how should I say, more simple than healthy organisms. So scale invariance, which is characteristic of those systems, is pointing out that the disease is coming when those fractal organization on several levels in physiology are breaking down because of some reason, because the neural signaling is not working, because something in internal regulatory system is not working. I'm not going to go there because, I mean, it is so wide field. But I want you to understand from the point of physics that if certain complex system is organized, it has certain internal mechanism how, for example, if you're out of the range, you come closer to equilibrium and things like that. So we know that certain pathological conditions are connected to breakdown of that complexity. Next slide. I think we have to accelerate a bit. Accelerate a bit. Next slide. So, for example, this is a good illustration of congestive heart failure. And you can see with the naked eye, you don't have to analyze that. The upper slide belongs to a normal person who doesn't have problems with the heart. And congestive heart failure is like a sinusoid. There is certain pathology which leads to this kind of signal, but you can also see that in apnea. If you don't have normal dynamics of breathing and synchronization with the heart dynamics, you have too simple signal to be healthy. I mean, those signals cannot synchronize, you cannot calm down yourself. You can also see that in mood disorders. You can see similar things in movement disorders. This is just in general, that there is a big difference between healthy signal and signal of someone who had certain disease. You can recognize that. So why we are doing that? Because we want to use technology to early detect something before someone has clinical signs. So because I already realized that we are over time, I'm not going to use all the slides that I prepared, but in general, I want you to understand that this kind of knowledge is giving you possibility to early detect diseases like Parkinsonism. For example, it is possible to detect Parkinsonism in early phase when you still can give some protective, neuroprotective drugs. Then mild cognitive impairment can be measured. I can show you some of the results later. And you know that this is considered prodromal phase of Alzheimer's. Then, for example, in depression, you can see how people progress, whether they are responders to therapy or electromagnetic stimulation, etc., etc. Also, it is possible to predict whether someone is having a seizure. For example, people who have multiple seizures during the day, you can actually prevent them of going somewhere, stay calm until it passes, etc., etc. Let's go some slide further. So, for example, this is a good illustration. Left is the picture how episeizure looks like. On the left upper slide, you can see EEG recorded when the patient had episeizure. When you calculate fractal dimension of that, you actually see below that system is too simple to operate. Its complexity is pathologically low. But this is not limited to human physiology. On the right side, you can see what happens with the market. Because if big collapse happens, the complexity of that system is too low to be viable. So it happens on many different levels, not only in physiology. Next slide, please. So this is a lot of different fields where I applied this kind of methodology. One is meteorological data, then hypoxia in infants, then in movement disorders, then recurrent spots in transcranial magnetic stimulation, transcranial direct stimulation, then in computational physiology, psychiatry. Then you can apply it in many, many different fields. So let's go further. I want to show you some results like an illustration. So this work is particularly important if you want to understand, for example, depression. So when they did an MRI study, they showed that connectivity between prefrontal cortices and limbic system doesn't have a normal signaling because deep white matter tracks are not functionally, they're not fully functional. For example, in healthy person who can have control of the affect. For example, prefrontal cortices can put down limbic system signals. People who have mood disorders simply cannot do that because they have only 65% of those connections alive. For some reason, they have lower connectivity. We don't know why. Next slide. And then I was thinking how we can quantify that. So basically, if you look at the blue dots, those are the patients. They exhibit the same features in their EEG. Red dots are people who are healthy. And we applied in that paper characterization of electroencephalogram by fractal dimension and sample entropy. And we use that as a feature for several different models of classifiers, which are used for all kinds of different things. And all of them actually showed quite big accuracy in deciding who is depressed and who is not, meaning that you can extract the features from our signals, which can serve for automatic recognition. Next slide, please. By the way, this is from the time when I have my company Triega in Holland, because we actually developed the software, how people can use that in psychiatric clinics. So basically, if you see this is another work coming from EEG studies, you can also see that they classify within the same disorder. For example, it looks different if people are in remission phase and if they are in episode. So this is also next work. You can go to the next one, where we actually successfully delineated those two phases of disease. Think about the clinician who can have that information and can say, okay, we are going to change therapy now because the patient feels better. Next slide. So another very important field in neuroscience is all kind of recording, modern recording that we have, like wireless EEG caps. You can use it to study a lot of things, not only movement. You can also look at the performance in sport, the children behavior, the way how they learn, the way how they're forming certain kind of knowledge and memories and things like that. So I highly recommend that you learn more about EEG, and especially in new technological advancements in that field. Next slide, please. So basically, we had one study when we wanted to see whether we can predict that bipolar patient will have mania, because this is important for family, this is important for the person to avoid some harm. And basically, we collected a lot of data, but it turned out that out of 168 different things we measured, only 2 turned out to be relatable to the task of prediction. And this is one, quality of sleep and irritability. And they're also connected, because if a healthy person is not sleeping well one night, tomorrow you're just a little bit irritable. But if a person has bipolar depression, this is a trigger for mania. So this is just one of examples that if you're engaging in research which is combining features of electrophysiological signal and machine learning, I highly recommend that you learn more about the features and whether someone did that before, because you can save yourself a lot of time. If you already understand that certain features are most important, focus on them. And on top of that, I forgot to say in previous research when we described in detection of depression, we also saw that complexity on cortex is increased in depressed people, basically on all the cap. So why recording all the cap? You don't need 64 electrodes. You can have 2 or 3, and then you will have the same level of detection. Next slide, please. So another step that I took is to understand why 2 most prominent NIBS technique, like repetitive transcranial magnetic stimulation and transcranial direct stimulation, are helping in therapy of depression, which is non-medication. Let's go to the next slide. Actually, what we did here, we recorded EEG before TDCS, immediately after TDCS, 10 minutes after that, half an hour after that. So the red dots on those graphs are the samples from before. Nothing happened. The green one is after the stimulation. The blue one is 10 minutes after the stimulation. The yellow one is half an hour after the stimulation. The pink one is 35 minutes after the stimulation. And you ask me, okay, so how do you interpret that? How do you define neuroplasticity? Neuroplasticity is change induced by something which lives more than half an hour, meaning that you stimulate the brain, and if after half an hour that change is still there, it didn't return to previous state, it didn't return to red state. It means that TDCS is actually able to induce some plastic changes in the brain. How you do that? You record EEG before intervention, immediately after intervention, and then later to see what is the extent of those changes. You can go to the next slide. This is also interesting work because we work with transcranial magnetic stimulation to compare that with peripheral nerve stimulation. And we actually showed with the complexity measures, you can see the graphs on the right, that after stimulation, all the signals that we measured, and we measured electromyogram in this sense because you have target muscle on your hand, they're always less complex. And then we were thinking how to understand that. Because, you know, EEG is composite signal. It is having under the cap electrical activity of everything which is below. Deeper structures, evolutively older structures, and you cannot interpret that from EEG because EEG is on measuring the cortex electrical activity. But you can see that that activity in person has certain dynamic, right? You measure and you see how that changes over time. But if you present strong electrical fields, that field actually introduces something which is disrupting activity, and then you see the fall in complexity. Can you understand that from graph? Yes or no? So,
Yes.
so basically what we figured out, in depression, you usually measure in their EEG that their complexity is higher. And if you play electrical field, it is able to actually lower that complexity. And it happens that after a certain number of those stimulations which are able to lower that pathologically high complexity, they feel better. Meaning that we understood why electromagnetic or magnetic stimulation works, because it is able to change that pathological complexity in people who are suffering from depression. Of course, like also electroconvulsive therapy, it has to be repeated over the time because the cause of depression is deeper deficiency or deeper aberration in structure, and you cannot change that with a stimulation. But obviously, they can benefit of that stimulation, which is repeated over time. Please go to the next slide. Okay, we can go further. We are in the end. So this is the paper which is explaining why those two kind of stimulations work well in depression. Can we go a little bit further? Okay, so I will just leave you with a question. What do you think? Because you know enough from medicine to judge. You already know that autonomous nervous system is very important, and it is not voluntary controlled, but it is in connection with prefrontal cortex. This is through cortico-autonomic network. So you can see why, for example, breathing and heart rhythm are connected. For example, if you're stressed, what you're going to do? You're going to do this, right? What you just did. You actually try to use breathing as a regulatory mechanism to slow down increased heart rate. And if you're healthy, that mechanism works, okay? In people who have, let's say, mood disorder or PTSD or ADHD, that synchronization is not optimal. So they cannot use normal ways of regulation on will, right? So basically, we already know for quite a long time that someone who has that sort of problems, let's say mood disorder or PTSD, they usually also have cardiovascular risk, which is not addressed. So basically, if you're a patient in Canada and you have heart attack, if you go out of ECHO, they immediately test you for depression. Why? Because if you have high cardiovascular risk and you have depression, you have 6 months to live. Because it is going to come again. You don't have regulation, right? So the idea is European Association of Cardiologists already recognized that in mood disorders and generally in majority of psychiatric disorders, we should take on eye also what happens with their cardiac health. Next slide, please. I did a preliminary, actually, this is a survey which shows us that this is true. In people who have depression and anxiety, you can detect cardiovascular risks. Why I mention women? Because women have higher prevalence to develop depression. From 5 patients, 4 out of those 5 are women. I'm not going to go into explanation. And also, because women have different clinical signs, they're undetected that they have a risk of cardiovascular disease. For example, female in large numbers are dying after first heart attack, and they have different symptoms. They don't have pain in the left hand. They have pain in the back or more in the jawline or things like that. Next slide, please. So basically, you can see from that paper, effect sizes, if you apply some of the nonlinear measures to analyze their ECG, are much more powerful for use. I'm not going to go into detail, but if you start learning about nonlinear analysis and you plan to do some neuroscientific research, it will pay off. Next slide, please. So I'm just going to stop here, but I want to explain this figure. Someone who know that psychiatrists know for quite a long of time that comorbidity is a big issue in psychiatry, actually compared something like 200,000 people. And they show that, for example, if somebody has anxiety, let's say like a teenager, they are most likely going to develop depression and vice versa. And you can see that between different ontologies, between different categorization, there are strong connections, like schizophrenia and bipolar. They actually look alike. Depression and anxiety, they have some same features. I'm just going to leave you with this because people who have comorbidities has to be the source of our future research, because probably our current classification is not good enough. And I would like to see in practice, I'm working on that, to introduce cardiovascular risk screening to psychiatric patients. So I don't know what you think about that, but I think it makes a lot of sense, because if you know that there is theoretical and anatomical proof that they go together, that they are comorbid, people who suffer from depression are not dying of depression. They're dying of heart attack. So you can save lives. If you do something about their cardiac health, you can also maybe improve the quality of life. And yeah, I see a huge perspective in this kind of research. And using AI, machine learning is good, but think about that you first have to know physiology very well before applying advanced statistical methods. So I would finish here because we don't have more time, but I hope you like the topic. I'm here for the questions.
Thank you for this great presentation. It's really caught my attention, especially the physical complexity part. I'm absolutely make some research about it. I have a question. Firstly, I want to ask that. So we mentioned about if something is complex, it means that the system is healthy. We can say that. So when we are measuring those signals, are there different thresholds for different systems, and how can we evaluate that measurements and classify them as complex or non-complex?
Good question, because you know, this research is not new. The mathematics behind that was developed 200 years ago. It is just that we had to wait for computers, powerful computers, that we can generate that. So there is not enough data. I can tell you where to look. For example, they first started using it in cardiology. And they already know, because this is easier signal to analyze in the first place. For example, in cardiology, complexity studies are used to detect, for example, arrhythmias, because based on less complexity or missing parts of the RQS code, you can see that something is wrong with the physical structure which is generating that signal. So I recommend, if you want to learn about that, to read the literature published in cardiology part, because I think they have the most material which is accessible and it is easier signal to understand. So basically, it is used for different kinds of detection. What does that mean, detection? Detection means it can be twofold. For example, I know that some people who produce portable devices are using deep learning to learn the normal morphology of the heartbeat and simply recognize if something is missing. This is a good way, for example, to detect really rare arrhythmias, because they are more than 20, if I'm correct. So some are more pronounced, some are not even possible to see with the naked eye. So basically, I cannot answer straightforwardly on your question, because, for example, in EEG, there are not enough data sets shared that you can learn on the big number of subjects. The bigger subset that I have is something like 3,000 people in ECG and something like 150 people in EEG. And if you're talking about reproducibility, we should always aim on the larger sample. And I recommend collaborative research with other people who maybe recorded something, but they didn't apply nonlinear measures. This is what I regularly do. For example, I have a colleague who is interested in the same topic, and they recorded some EEG, but they analyze it only with standard measures, which are really misleading to interpret. And I asked them, are you interested to analyze entropies? For example, maybe we can squeeze something from your data. So basically, they are not pronounced standard biomarkers yet, because for that you have to have enough cases where you can do stratification and recommend that as acceptance. But I know myself from my previous research, from data sets that I already saw, what can be in certain things pathological. For example, we had a data set for people who are older. Older means older than 75. And they were considered to be healthy. But when they recorded ECG, EEG, and other things, and when I analyzed that, I actually saw in their signals that the complexity is that low that they probably already have mild cognitive impairment. And when I talked to the neurologist who was taking care of those people, because it was recorded 3 years before, meanwhile, they already developed some symptoms. So we could see that, for example, mild cognitive impairment can be, you can search my publications online, because we just published last year that we detected mild cognitive impairment from the low complexity of their EEG. This is not a big sample. Now we are trying to repeat similar results on the largest sample, and then we might say that it can be standardized. But at the moment, this is not so popular study direction. I think we are getting steam because younger people are enthusiastic about that. You can calculate it in real time. And I think we will see next 5 years, maybe even a software which is publicly available, or databases that you can use for study to adopt the same kind of approach if you're studying either heart or muscles or brain.
Thank you for your explanation. I will look to your publications for further explanations. And I want to ask a question from our YouTube live presentation. You said we can regulate biological signals. How exactly do we do this?
Well, one example I gave you, the synchronization flip-flop between heart and breathing already exists. And for example, if you read the work of Bessel van der Kolk, which is the most prominent researcher in PTSD, he actually discovered that people who have serious PTSD disorder, they don't have that regulation at all. For example, they start panicking and they cannot simply calm down. So that can be seen also in other psychiatric disorders. For example, people who have anxiety, people who have depression, because one of the features of depression is that people cannot disengage from negative content. And when we are healthy, we can control that. We can distract our attention from something negative to something else. So when I say regulation, I think about that. So this is not just one thing. When we regulate ourselves, maybe I should say we can calm down. How someone can calm down? For example, you can try to relax. You can wash your hands. You can have a warm bath. You can start breathing a specific way. You can go and walk. All those are natural ways how we calm ourselves. And if you see in the trends in psychiatry, what they're recommending to their patients, instead of relying only on medication, is to find out what works for them. Someone is calming down when they're listening to the music. Some can calm down when they're sing. So I can attract your attention as neuroscience students why those things. For example, prosodic voice is connected to the functioning of the vagus nerve. How we calm down with other people. You are observing their eyes and you're signaling the movements of their eyes, what they are signaling, whether they are safe or not safe. You can recognize it automatically. Then the next thing is the sound. If some sound is threatening, like very deep, very unknown, dangerous, then the female voice, which is soft, can calm you because of how vagus nerve is functioning. Also, physical activity can help you calm because of the, bigger perfusion of the blood and much better functioning of the brain if you have more oxygen in your blood vessels. So basically, if you're interested in how we calm down to yourselves, I can recommend two authors, most prominent in that kind of research. One is Bessel van der Kolk, who is writing about PTSD, but I mean, this is extreme case. We can all learn how we can calm ourselves. If something is working for someone who have PTSD, it works for much smaller problems as well. And the second author I would recommend is polyvagal theory author. His name is Stephen Porges. And he wrote about little known 3 levels of mechanisms characteristic for vagus nerve, which are corresponding with our evolutionary development or our brain. Because, for example, in those patients who are extremely sick and cannot regulate, they have fight or flight or freeze or dissociate. Those 4 levels of escape are actually all connected to the levels of vagal control, because if something is really dangerous, you have energy in your system and you switch to that mode that you can fight. You have energy to fight, or you can run to save yourself. If you cannot physically remove yourself from the situation, you can freeze. Look at the animals. They play dead. This is the same mechanism. And dissociation, if a big harm is done to you, you don't know about that. Because the philosophy of our protective mechanism are really wise. They're preserving life. If something really terrible happens to you, it is better that you forget that. So people who have really serious trauma actually don't remember that. They survived, but then the role of psychotherapy is to help them, develop behaviors and patterns to live normal life after that. So basically, I would direct you to learn more about those control mechanisms like vagus nerve regulation, like polyvagal theory, like PTSD, because if you understand that, you can understand the mechanisms that we are using every day and we are not even thinking about that.
Okay, thank you. So we have another question. This is the last one. What do you think about the future usage of EEG beside you told in this presentation?
Oh, there are many, many uses. For example, EEG can be used in neurofeedback. I'm really big fan of that because you basically can modulate your brain with that feedback. And this is used in many therapies like ADHD, depression, PTSD, whatever. Read about it. Second thing, I mean, what is made for people who are sick can always be used to enhance our abilities as human beings. For example, your cognitive abilities, your precision like a musician, your how should I say, abilities like an artist can be also used by help of feedback. You can use neurofeedback not only because you have disorder, you can use neurofeedback to learn something new, because neurofeedback is actually enhancement of learning mechanism. How we learn, we repeat things and we become better in doing that. And when you learn something, it becomes automatic. Not a big difference. Then we can maybe do some automatic control based on our EEG. For example, this is the brain-computer interface. Again, it is developed for people who are paraplegics or quadriplegics and things like that, or people with locked-in syndrome, but it can be used for video games. It can be used for all kinds of controls. So I can see more of that because people like to play with that, although it doesn't have to be just a therapy. Then, for example, if you're training something, if you're into sport, or if you want to enhance somebody's abilities, you can also use EEG. So EEG can be used not only in diagnostic and treatment. I'm also a big fan of using EEG for other purposes, and I can see a lot of that coming. For example, if you see EEG caps that I show, half of them are actually developed for gaming. So you can learn how to translate your motor commands into something which is not your own movement, but in your surroundings as well. So this is also extended memory concept, which is learned in robotics as well.
Thank you for these explanations. We would like to introduce your certificate for this presentation. Again, thank you for your acceptance and thank you for being here with us today.
Okay, thank you. I hope you will use something, at least something that you learned from me. Okay.
We will. Thank you so much. We will also mail this to you.
Okay.
The certificate.
Okay. Thank you very much.
Thank you.
Have a nice evening.
You too.
Bye-bye.
Thank you. Bye.